I want to talk about nuclear power, and specifically a type of nuclear reactor that's never been fully developed, different from the one that's presently used in nuclear power generation, based on the element thorium. A lot of engineers feel that there are a whole lot of advantages of this type of nuclear reactor over the one that's being used today. Like, for instance, the fuel is far more abundant than uranium-235, which is used today. There's supposedly enough thorium in this one deposit in Idaho to power the United States for 1,000 years. And so it's a much more abundant nuclear fuel. It's probably safer than the U-235, it appears definitely to be a safer kind of nuclear power. There's a small amount of nuclear waste. You can build smaller reactors, which make them more applicable to different kinds of uses. And there's just a whole bunch of advantages. The kind of reactor that's used now is called a pressurized light water reactor. In the core of the reactor, there's a whole lot of uranium-235 fuel in a solid form. And that's surrounded by highly pressurized water. And those factors introduce intrinsic risks to this type of reactor, especially the pressurized water, because that water can leak out and you can get radiation leaking out. So U-235 is the fuel. But then I want to talk about use of thorium. The fuel is in a liquid form. It's dissolved in a molten salt. And there's several different molten salts circulating in the various parts of the reactor. But the design of the reactor pretty much eliminates the possibility of any of these bad kind of nuclear accidents like the ones that we've had. A little bit about the world's energy consumption. It's on the order of hundreds of millions of trillions of joules per year for all the energy used by mankind. And you can see the U.S. is a pretty big chunk of that. But countries like China and India will vastly increase their energy usage in the future. And them, and probably all these countries, will choose the cheapest kind of energy available. At present, they have coal. And it would be a good idea to get away from coal because not only is that an exhaustible resource, but it dumps CO2 into the atmosphere, and there's numerous problems because of that. So it would be nice to have an energy source that's cheaper than coal. In Georgia, this is just electricity usage now, but about 3/4 of the electricity that we use is generated using the burning of fossil fuels, primarily coal. So Georgia would be a perfect place to find a cleaner energy source that is cheaper than coal. And of course, one of the reasons we want to get away from the use of coal is that it's adding CO2 to the atmosphere. This is the CO2 level in the Earth's atmosphere in parts per million. And it's been steadily increasing, which could very well cause some bad climate problems. One of the lesser-known things is the CO2 content of the ocean water is also increasing, and that is lowering the pH of the ocean water. It's becoming more acidic. And we're already seeing effects of that. More serious effects could happen later on if the pH gets low enough. There are these microscopic creatures that form the base of the food chain in the ocean, and they're calcified shells, which may not be able to form in a pH that's too low. So the CO2 content of the atmosphere has been way higher in the distant past of the history of Earth, but it's probably never gone up this fast, so the Earth may not be able to make up for that. Anyway, those are some of the arguments for getting away from a CO2-producing energy source. Now, of course, renewable energy is part of the solution. Both wind and solar power are far cheaper than they used to be. But these are energy sources that are very diffuse. In other words, the energy is distributed very widely in the atmosphere, so they require a lot of generators to collect it. And they're also intermittent energy sources. The sun doesn't always shine, the wind doesn't always blow. So you need far more generators than the total load that are operating at full power at any given time. And you need a very complicated power transmission system to carry the electricity from where it's being generated to where it's being used. So it may not be possible for these renewable energy sources to ever get cheaper than coal, which means, even if we committed ourselves completely to the use of renewable energy, countries like China and India that that are just getting started and don't have the resources, will probably choose coal over these. And so it would still be better to have an eco-friendly solution. Now here's the kind of thing you don't want to happen with nuclear power. This is the explosion of one of the containments around a reactor at the Fukushima plant in 2011. There was the Honshu earthquake, this enormous earthquake, caused the reactors to strand, to shut themselves down. And the fission reaction stopped, but in the present kind of nuclear reactor, the fission products are still in there. They're very radioactive and produce heat, so you have to have power to heat the coolants supplied to the reactor, or it'll overheat. And so they have diesel generators. Well, then a tsunami caused by that earthquake came on shore and drowned out the emergency power supply. They had no power to the reactors, and they couldn't supply coolant water, and they had melting in 3 of their reactors, and one of the containments around the reactor exploded. And there was a big release of radioactivity. This kind of accident couldn't happen with the kind of reactor we're talking about, because for a number of reasons, one of which is the fission products are removed from the molten fuel as it's being produced, because it's a liquid. It's not solid. It doesn't have to stay in the reactor until you take the solid fuel out of there. It's constantly cycled in and out of the reactor. And the other, even worse accident occurred in 1986. One of the reactors at the Chernobyl plant in Ukraine, there was actually a runaway fission reaction, and the thing melted down and exploded, and there was an enormous release of radiation. Ultimately, 500,000 people were displaced from the region around the plant, and that is still evacuated. There's some people living in it, but they call it the Chernobyl exclusion zone. There's no one living there. The wildlife is doing great because there's no people there, but all these people were displaced because of this accident. And this kind of an accident couldn't occur with a liquid fuel reactor for a number of different reasons. Now, if these words like fission and fission products and all that stuff are confusing, if you don't know how nuclear power works, I'm going to talk a little bit more about that as I go on in this. But these are the kinds of things that you want to get away from in nuclear power. Now, why is nuclear power so energy dense? Why does the fuel contain so much more energy than chemical fuel? The reason is because the nucleus of atoms are something like 100,000 times smaller in diameter than the whole atom, than the part occupied by the electrons. So this dot is actually drawn about 1,000 times too big in diameter to accurately represent the size of the nucleus. It's that small. Well, that means the particles that comprise the nucleus, protons and neutrons, are hundreds of thousands of times closer to each other than atoms are to each other in molecules, which means that the binding energies that hold them together are hundreds of thousands or millions of times greater than the binding energies of molecules. And so in a typical chemical reaction, which is supposed to be methane, like your oxygen molecules, in the combustion of methane, these atoms dissociate from each other and form different molecules, like carbon dioxide and the waters. And these have a different binding energy than these. The difference is the energy that's released in the process. So that's when you burn methane, you get a flame, right? That energy of the flame is due to this difference in the binding energy. So in this process, the nuclei of these atoms don't change at all. They just mind their own business at the center of the atom. But in a nuclear process, there's a change in the constituents of the atomic nucleus. And the binding energy is hundreds of thousands of times greater, so the differences in binding energy during the change are way greater. That's why nuclear power is so much more energy dense. And to understand nuclear processes, it's helpful to introduce what's called the Segre chart. This is to nuclear physics sort of what the periodic table is to chemistry. On the periodic table, every square represents an element, right? Here, every square represents an isotope of an element. So this is a much larger chart. I'm only showing part of it here. And in here, the vertical position of the square signifies the number of protons in that isotope's nucleus, and the horizontal position, the number of neutrons. So for instance, carbon-12 has 6 protons, 6 neutrons, for a total of 12 nucleons. And carbon-13 has 6 protons, 7 neutrons. Carbon-14 has 6 protons, 8 neutrons. So you see that every row of this gray chart represents an element. These are the different isotopes. Now the black squares represent stable isotopes. Nobody's ever seen a carbon-12 nucleus spontaneously switch into a different isotope. That is called nuclear decay. But carbon-12 and carbon-13 are both stable isotopes of carbon, so they remain, as far as we know, forever. But carbon-14 is unstable, and eventually all the carbon-14 nuclei that exist right now will decay into nitrogen-14 by beta decay. And I'll talk more about the different decay processes that occur. But most of these white squares, almost none of them exist on Earth because they're unstable. They're radioisotopes, and they eventually change into stable isotopes. We know about them through nuclear experiments. And we know that these all can exist, but they don't exist in nature, most of them. Here's the whole gray chart. The slightly different color scheme. The yellow ones are radioisotopes, unstable isotopes, and the light blue are stable isotopes. So almost none of the radioisotopes exist in nature. But here, pink squares are radioisotopes which are nearly stable. They have very long half-lives. That's a measure of how unstable a radioisotope is. The longer the half-life, the more stable it is. The amount of time that it takes for half of it to go away. But you can see there's a number of these long-lived radioisotopes that exist in nature, even though it's been 4.5 billion years since the elements that make up the Earth were formed. And I want to point out these right here. They're very heavy, right? They have lots of neutrons, lots of protons. So these three isotopes are thorium-232, uranium-235, and uranium-238. Those are the three heavy isotopes that exist on the Earth. They're relatively long-lived, and all three can be used in nuclear power. And so that's want to sort of put them in context of the gray chart here. Now I'll talk about some of the nuclear decay processes that occur in nature. One of them is alpha decay, in which an alpha particle, 2 protons and 2 neutrons, comes zipping out of the nucleus. And this occurs because the final product, the separate alpha particle and smaller nucleus, has a more stable configuration of these particles. It has a higher binding energy, and the difference in binding energy is the energy that comes out. By the way, that energy comes out in the form of the kinetic energy of the alpha particle mostly. So this is one of the processes of nuclear decay. And on this gray chart, the yellow squares are the isotopes that mostly decay by alpha decay. Many of the isotopes can decay by more than one different mode, but these ones mostly decay by alpha. And you can see it's mostly the ones to the upper right, the heavier isotopes. Another type of decay is beta minus decay. In this, a neutron switches into a proton. There's one of the basic forces of nature is called the weak nuclear force, and that can cause protons and neutrons to switch into each other. So there's this mode that can occur. And in beta decay, a neutron switches into a proton, an electron comes into being, and also the anti-neutrinos. But the pink squares on this gray chart mostly decay by beta decay. And that should make basic sense because the pink squares are to the right for the stable isotopes, which means they have more neutrons than do stable isotopes. And so you might get that a more stable configuration would occur if some of those neutrons switch into protons. Right? There's lots of squares here. And what you do is one will decay to the square to the upper left, right, and just keep going until it reaches a stable nucleus. So these are all beta decays. So beta minus decay is where a neutron switches into a proton. Beta plus is, anybody guess? If beta minus is where a neutron switches into a proton, beta plus might be which a proton switches into a neutron. And so the blue ones are beta plus decayers. And so they're moving this way toward the stable isotope. So between alpha and beta, that's most of the squares on this gray chart, right? Most of these isotopes will decay by one of those modes. But there's a couple of other colors here. And the one I want to point out is the green colors right up here. That is called spontaneous fission. And in spontaneous fission, a large nucleus splits into two large pieces. Now on this diagram, they're exactly the same. They're almost never exactly the same, which is kind of a bad diagram. But it splits into two large pieces plus a couple of free neutrons. And the only ones, this almost happens not at all in nature. The three isotopes that I mentioned, the thorium and the two uraniums, are like right here on the secret chart. They're alpha atoms. A tiny fraction of them decay by spontaneous fission, but almost never. The only ones that decay primarily by spontaneous fission are the ones that have been artificially produced in nuclear reactors. But this is the process that's used in nuclear power because, I'll show you how that works. If say, an uranium-235 nucleus absorbs a neutron, it becomes uranium-236, which is also not a fission. But the absorption of the neutron bumps the nucleus up into a higher energy state, which is very unstable for fission. And that undergoes fission within parts of the neutron. And if you have enough of these U-235 nuclei in close proximity, one of these neutrons or more can be absorbed by another one, causing a chain reaction. So if you can moderate the flux of neutrons in the reactor, you can control the rate of this reaction. There is a nuclear process for which we can control the rate of it. Those others, alpha and beta, they pretty much run at the rate that they want to, and there's nothing you can do about it. But here's a way to control the nuclear process. And this was discovered in the late 30s, and of course it led to nuclear power and nuclear weapons, which were developed in the Second World War. So this is how nuclear power and nuclear weapons work. Now, here's the part of the severity chart to the way upper right containing those three radioisotopes that exist in nature. Only uranium-235 is fissile. In other words, only uranium-235 will do that process that I just showed you. But these, thorium-232 and uranium-238, you can use them in nuclear power in a somewhat more complicated way. If, for instance, thorium-232 absorbs a neutron, it becomes thorium-233, which will not fission, but it will beta decay into protactinium-233 with a relatively short half-life, and that will beta decay into uranium-233 with a relatively short half-life, and that is fissile. In other words, if that absorbs another neutron, it will undergo fission. Likewise, uranium-238 can be used to breed, as they say, plutonium-239, which is fissile. And in fact, this is the stuff that they use in nuclear weapons. So they can turn U-238 into plutonium-239 for use in nuclear weapons. But you can build a power reactor. They call it a breeder reactor because what's going on inside the reactor is a little more complicated. From the fissions that are going on in the fissile material, some are breeding more fuel nuclei, and some are causing fission. So notice, in this kind of reactor, at least two of the neutrons that are coming from every fission have to be absorbed by other nuclei in order to sustain this chain reaction, right? With the U-235, only one is needed, but here you need at least two of these neutrons to actually be absorbed by these other nuclei in order for the process to be sustained in undergoing a reactor. That is the primary reason why only U-235 is used in nuclear power, because this is a harder kind of power to make happen, because you need twice as many of the neutrons to actually be absorbed by other nuclei in order to make it work. So this is what occurs in a breeder reactor. Now, I'm going to show you kind of a technical diagram here. This is for the three isotopes, U-233, U-235, plutonium-239. This shows the number of neutrons that come out per neutron absorbed. And you can see that they kind of hover around 2, a little bit above 2 neutrons per neutron absorbed. So that means there is enough neutrons coming out of these in order to sustain the chain reaction, given that you need 2, okay? But the horizontal axis is the energy of the absorbed neutron. In other words, the number of neutrons you get out depends on how fast the neutrons that are hitting the nuclei are going. So for fast neutrons, it's a lot. The faster the neutrons, the more neutrons come out, and the better chance you have of sustaining this chain reaction, which requires 2 neutrons per fission. Now, when fission occurs, the neutrons are moving very fast. It's a nuclear process. Everything is energetic. So the neutrons are moving very fast. So you might say, well, great. I mean, if they're moving fast anyway, we have plenty of neutrons that can sustain a chain reaction. There's also disadvantages to this, though. And that is before I show you this is the Morris chart, I'll tell you about it. The neutrons, as they move through the reactor, the size of the nucleus that they see, they call it the absorption cross-section, depends on how fast the neutron is going. And a figure for slower moving neutrons. So here's the slower moving neutrons. They're great big targets. If you're a neutron moving through a nuclear reactor, how big a target do you see when you look at the nucleus that you want to be absorbed by? How big is the dartboard? And they're hundreds, it's a logarithmic scale, they're hundreds of times greater for slow neutrons than for fast neutrons. In other words, the chances, as the neutron is moving through if it's moving fast, going through the reactor, the chances of it being absorbed in a given volume of fuel are small. If it's moving slower, they're greater. That means you need a bigger reactor if the neutrons are moving fast. It limits the minimum size that you can build a reactor. So slowing down the neutrons makes it more possible for them to be absorbed. And in the reactors that are used today, they slow them down. They use what's called a moderator. And the moderator in the light water reactors is the water. The neutrons bump into the hydrogen nuclei that are in the water molecules, and that they lose energy to them when you slow down. So the neutrons are moderated. And so they call them thermal neutrons when they're slowed down. And you can see for the thermal neutrons, U233 has the most neutron yield per neutron absorbed. And that's what breeds from thorium-233, U233. And plutonium-239 has a smaller neutron yield, probably makes it impossible to use thermal neutrons in a U238 nuclear reactor. In other words, the process won't be sustained. For fast neutrons, plutonium-239 yields a lot of neutrons. And in the 1970s, there was research done on what they call the fast breeder reactor, which used U238 as the fuel, bred plutonium-239, and generated power that way. So you can build a fast breeder reactor with uranium-238, but it has to be very large because the fuel mass has to be very big so that the neutrons will be absorbed before running all the way through and leaving the reactor. That's one of the disadvantages of the fast breeder reactor. And now let me go through a couple of advantages of this thorium breeder reactor over the present type of uranium light water reactor. It's the abundance of the fuel. Can anybody see the piece of pie that represents U235? U235 is far less abundant than these other two isotopes, and it's because it has the shortest half-life. Its half-life is 700 million years, but that's 6 times shorter than the age of the Earth. And if you plot this Venn diagram for when the Earth formed, it's a significant amount of U235 back then. But it's been through over 6 half-lives, so it's down to 1% of its original abundance. So there's very little of this 235, and this is the isotope that we use in all nuclear power on Earth. All the power generation, all the nuclear reactors on Navy ships and so forth, use that stuff. So this is a major disadvantage. We have lots more thorium now, and we basically have thousands of years worth of thorium, but maybe a century's worth of U235. Nobody's really sure how much. Now another disadvantage of the light water reactor is this is on these containments around the reactor. The reactor is actually very small inside of here, but you need this enormous and extremely strong containment because there's pressurized water in there. If that water leaks out, you have to be able to contain that because it's radioactive. you can't let that escape. And so you need this enormous, extremely strong containment around there. And that's very expensive to build. And of course, sometimes it doesn't work. The Fukushima plant, one of these actually exploded, releasing that radioactive steam. So it was a very expensive plant to build. And in the reactor, it goes, no, it doesn't explode, but it's, it releases radiation into the environment. And right now, the wind was blowing in Japan. That plant was on the east coast, and the wind was blowing toward the northwest. So there was a sweep of radiation across this region, and people were evacuated out of that region. I don't know if there have been any measured health effects due to that radiation so far. That's your
What do they have exactly the people if there's not any health concerns?
Well, there are health concerns. They're very serious health concerns.
What could be a health concern?
It can cause cancer. After the Chernobyl accident, there was a rash of thyroid cancers because one of the fission products is radioactive iodine, and iodine, okay, is this right? Iodine is absorbed in the body and goes straight to the thyroid and can cause cancer there. They give them salt pills with iodine in them, with regular iodine, to sort of saturate your thyroid with iodine so it can't absorb anymore from the air. But there were like thousands of thyroid cancer cases after Chernobyl. I don't know what's happened in Japan. The response to it was better in Japan than it was at the Chernobyl plant. But yeah, it's very serious. So you don't want to call them. So this is what like basic schematic of a light water reactor. There's solid U-235 fuel in here, and these are control rods. It's the material that absorbs neutrons but doesn't undergo a nuclear process. And when you have those in there, the neutrons coming out of the fissions are absorbed by these, and they can't go into sustaining the chain reaction, so the reaction stops. And when you pull those rods out, then the reaction speeds up because the neutrons are then available to sustain a fission chain reaction. But there's always the possibility for the reaction to run away from you, and that's what happened at the Chernobyl plant. It shouldn't have happened, but they broke a bunch of rules during that, of all things, a safety test of the reactor, and the reaction got away from them. So it is a bit of a balancing act, and if you lose your balance, there's very serious consequences. But this kind of balance, if you don't have this, there's no possibility of a runaway reaction with the liquid fuel reactor for reasons having to do with the dynamics of the fuel. Here's a major disadvantage of the present light water reactors. When you get uranium out of the ground, it's almost all uranium-238, and that does not burn in the nuclear reactors. You need the 235. So they enrich the uranium in 235. They condense it in 235. Now, separating isotopes of the same element is very difficult. It's much more difficult than separating elements from each other because the two isotopes are essentially chemically identical. And it's very difficult. So this is a very expensive process to enrich the uranium in 235. But once it's enriched, it goes into the reactor, stays there for 18 months or so. And when it comes out, you still got that 238, which hasn't done anything. And the solid fuel reactor is also relatively inefficient. And so you still have some 235 left over that didn't undergo fission. Then there's the fission products, the U-235 nuclei that did fission. And then there's a significant amount of heavier isotopes. These are the ones that have the really long half-lives that are the reason that this radioactive waste is going to be around for tens of thousands of years, and it's going to be radioactive for that whole time. It's these things. They mostly form when the U-238 nuclei absorb neutrons and become heavier isotopes. So now this actually can be separated. It's possible to separate these out, and this stuff is not radioactive because it's just, well, it's radioactive, but it's no more radioactive than it was when you got it out of the ground. And you can reuse the 235, and most of these have a relatively short half-life, so they're not as bad. But, I mean, it could be separated, but so far that has not been done. But contrast that with thorium. There's only one isotope of it. You take the 1 ton of thorium out of the ground, it goes in the reactor. Almost all of it undergoes fission in this process. And most of that will decay to stable isotopes. In other words, the fission products will decay to stable isotopes inside of 10 years. But some of it will still be radioactive for a couple of centuries. Now, a couple of centuries is a long time, but it's not 10,000 years, right? I mean, I actually know what some of my ancestors were doing 300 years ago, but 10,000 years ago we don't know what anybody was doing. So that is not a time scale over which you can ensure that this stuff will remain, intact. And it's very little of these heavier isotopes. So it's, it's a much cleaner, and it's just the mining question right there. You have to take much less stuff out of the ground. And in fact, thorium is the byproduct of some mining operations right now, but it's not used for anything. It can be used as nuclear fuel, but there's thousands of tons of it sitting out to the side. Now, another advantage is the reactor can be made small because of the thing I was talking about earlier with the thermal neutrons see a larger target in the nuclei. The whole reason this reactor design exists is because back in the 1950s, the U.S. Air Force wanted to build a nuclear-powered bomber because that was before the age of ICBMs, and the best way to get a nuclear warhead to the Soviet Union was to carry it in a bomber. And they kept these huge bombers in the air. They would fly them from like Kansas up to the Arctic, so they'd be near Soviet territory in case, they got a call from the White House to bomb the cities. But the airplane wouldn't be able to stay very long, and then it'd have to be relieved by other bombers, which would have to fly all the way to Kansas. And it was a very, these airplanes had to be in the air for a long period of time. And the Air Force thought, well, wouldn't it be nice if we had an airplane that could stay on station near the Soviet territory for a month and then come back and be relieved by another bomber. So they wanted a nuclear-powered bomber. And the engineers that were working on this looked at different designs for nuclear reactors. There's many different ways, many different designs for a nuclear reactor. They looked at the light water reactor that we use in power and was already running nuclear submarines at the time. But it was too heavy because it's a pressurized reactor and it has very heavy cladding and everything. So it was just impractical for an airplane. They looked at all these different designs. The one they settled on was the thorium reactor based on a molten salt liquid fuel because it could conceivably be light enough to apply to power a bomber. Eventually, it became clear that even that was impractical, that it wouldn't, they'd never see a nuclear-powered bomber fly. But the engineers were very intrigued by this reactor design for its application to power production. And in many ways, it lends itself much better to power production than does the light water reactor. It was originally designed for nuclear submarines and just adapted to power production. So that's where this all comes from. So the fact that these reactors could be built smaller means that you could use it in smaller naval applications, just as a modern destroyer. The only Navy ships that are powered by nuclear power are the huge aircraft carriers and some ballistic missile sites, because ships this size just don't, the light water reactor just doesn't lend itself to that small application. But the Navy would love to have a ship that's nuclear powered that's one of their smaller vessels. And so the thorium reactor might be applicable to this sort of thing. And then for that matter, civilian ships, all kinds of ships could be powered by this relatively small reactor. Now, another neat thing about these molten salt reactors is that they operate at a very high temperature. Salt melts at maybe 500 Celsius, depending on the salt, but it doesn't boil until like 1500 Celsius, so there's a huge range of temperatures in which it's liquid. and you can operate the reactor at a very high temperature. The reason a light water reactor is pressurized is because the coolant is water. Water boils at 100 Celsius. To make it boil at a higher temperature, you got to put it under pressure. So they don't operate at high enough a temperature. The advantage of operating at a high temperature is because you have a better thermodynamic efficiency. In other words, the higher fraction of the energy, the heat energy, winds up doing what you want it to, like generating electricity or driving the chemical process. And there have been discussions of driving chemical processes with the heat from these thorium reactors. For instance, you could dissociate water into hydrogen and oxygen and use the hydrogen in fuel cells, like in fuel cell cars. Or it's even been discussed that you could generate dimethyl ether, which can be used in diesel engines, or methanol, which can be used in gasoline engines. The idea being you'd take CO2 out of the air, use the carbon and oxygen from that CO2, and drive chemical reactions using the energy from the reactor, and actually make fuel that we could use in the vehicles that we have now. I don't know about the practicality of that. I mean, CO2 is still a trace gas from the Earth's atmosphere. I don't know how practical it really would be to make liquid fuel for vehicles from consistently air. But this kind of high temperature reactor, I guess, lends itself to these kinds of chemical generation applications better than like a light water reactor. Now, another thing that intrigues me about this type of reactor is the fissile isotope is U-233. So that absorbs a neutron and they fission, but not all of them do. Some of them don't undergo fission. That absorbs another neutron in the reactor. It becomes U-235, which of course is fissile. That's what's used in the present-day reactors. So that can absorb a neutron and undergo fission, but some of them don't undergo fission either, which means that it's 236. If that absorbs another neutron, it's 237. Ultimately, it becomes plutonium-238, and this is the primary heavier waste product from these thorium reactors. But this stuff does not have a half-life of thousands of years. It has a half-life of like 60 years. And it's the ideal fuel for these space probes. This is the Cassini probe that's orbiting Saturn. It's been orbiting Saturn for about 10 years. And it has 75 pounds of plutonium-238 that powers all its instruments. So hundreds of watts of power. And that's how it will be observing and send data back to the Earth. So plutonium-238 is about the only one of these heavy isotopes that can be made or dug up that lends itself to nuclear power in spaceflight. And if we ever want to go into space in a real way, the spacecraft, both manned and unmanned, really need to be nuclear powered. And this is the only viable fuel for it. So the primary waste product can actually be used as a fuel for spacecraft, which is pretty intriguing. Now,
the fuel eventually run out.
Mm-hmm.
We have to put it back there and do it again and then.
Well, with Cassini, it'll never come back to Earth. It'll eventually be dumped into the atmosphere of Saturn when it's done its mission. It's going to be running for another couple of years or something. It's been there 10 years. But that power, like the Voyager probes that have been going since 75 or something, they're still running on those plutonium power sources. So that the amount of it has dropped down, so the power output has dropped down. But these are for power sources that you don't want to have to refuel. You want them to keep going for decades unrefueled. And the only way to do that is nuclear power. For manned space flight, it's advantageous to use nuclear power for slightly different reasons. But this is the nuclear power source that really kind of lends itself best. Here's a great chart, and the color here indicates the fission product of U-233. So where the black squares are, that means a lot of it is produced, and the other colors not so much. So U-233 is somewhere up there. these are the isotopes that are produced. So a whole lot of isotopes are produced in nuclear fission because the nuclei split apart into humps of different sizes. And these have to be actively removed because some of these isotopes actually absorb neutrons pretty well and will suck the neutrons out of your chain reaction and cause them to occur. That's the main reason why the liquid fuel idea was developed, because in order for this breeder reactor thing to be sustained, we need 2 neutrons per fission to be absorbed. You have to remove those other things that are going to take the neutrons away from the chain reaction. So you have to remove some of these fission products in order to get that stuff out of it. But some of them are actually useful. And this one right here is molybdenum-99. That decays into technetium-99, which is actually used in medical imaging. And as it happens, I had one of these medical imaging things done a couple of weeks ago. They inject you your bloodstream with technetium-99 as a 6-hour half-life, and then they get into gamma rays. It's technetium-99M. But these gamma rays put you inside this big gamma ray camera, and they actually see the blood flowing through your coronary arteries. There's some reason to believe that I have blockage in my coronary arteries. So that's how they check out whether you have blockage in your coronary arteries. It's very commonly done medical imaging method, and the isotope that they use, technetium-99, comes from the waste products of nuclear reactors. So that's one of the isotopes that's actually useful. They can be separated out from these things. Most of these products are they decay to stable isotopes within about a decade or something. But you know what I was saying earlier. Now, let me talk a little bit about the basic architecture of these reactors. So the breeding process, the thorium-232 nucleus absorbs the neutron, becomes thorium-233. It has a short half-life. It's under a 22-minute half-life, so it very quickly turns into protactinium-233. That has a longer half-life, 27 days. And for that reason, for most of these reactor designs, it needs to be removed from the reactor because if that absorbs another neutron, it becomes protactinium-234, which doesn't fission and can eventually lead to some fissile isotopes, but will absorb, in most cases, will absorb too many neutrons in order for the chain reaction to be sustained. So many of these reactor designs, this is the basic setup. Here's the core where the U233 fission occurs. The neutrons are causing the fission chain reaction. Some of them are coming out to this blanket, which contains thorium, which is absorbing them and becoming thorium-233. These then decay into protactinium-233, and since it's a liquid fuel, the stuff is dissolved in a molten salt. It goes through a chemical extraction process which removes the protactinium from the thorium. It's now a different element, so it's more extractable than two isotopes of the same element. And then kind of the way they want to do this is there's apparently these two elements have different solubility in the salt, and so it can actually cause a precipitate out. So anyway, it's removed from this, and then it sits in a decay tank until it turns into uranium-233 and it's extracted from that. Then it goes into the core and is the fission fuel. So it's produced, the thorium is bred into uranium by absorbing the neutrons in the blanket. And so all three of these systems, the blue and the pink and the purple, are different molten salt cyclic systems where you can pump this stuff around. Now the neat thing about some of these liquid fuel reactors is the fuel itself can be pumped out to extract the heat to run the generators. So the fuel itself gives the coolant. In the light water reactors that we have now, the coolant is water. So that there's no need for a separate cooling system because the fuel is liquid. So that the heat comes out, and then it can also be cycled to the place where the fission products are removed by these different chemical separation processes. So this is the basic setup. And in some of these, apparently in some of these designs, they don't include that step. So I guess enough of the protactinium behaves into uranium in the blanket without becoming protactinium-234, where you don't need that extra stuff. So there's various designs that we can do. But there's a kind of neat diagram showing the mixture of salts that people want to use for the liquid. A combination of sodium chloride, potassium chloride, and lithium chloride. And the combination that they've mentioned is this one here, they call it Flynac. It has a melting point of 454 Celsius, and then have a boiling point of something like 1500 Celsius. There's a wide range of temperatures for which it's liquid. And this is the kind of material that the fuels in these various salt systems would be dissolved in. So there are technical challenges to this. These numerous chemical separation processes have to work in order to take the protactinium out of the blanket salt, take the fission products out of the core salt, and those have to be able to run real time. There's also, since the high temperatures inside the reactor, there's also some pretty serious corrosion problems. For example, the moderator, the material that's used to slow down the neutrons, is graphite. And graphite apparently is badly damaged by the high temperatures. So there's serious technical problems that have to be worked out. And so this kind of technology development program is one that lends itself to the huge resources of a thing like the United States government. So it's something that it should probably be initiated by the Department of Energy or something like that. But so far there hasn't been very much interest in that. So I thought if they did this, we could potentially have an eco-friendly, very clean source of energy that's essentially inexhaustible. So that's what I got. Thank you for coming. So, are there any questions? You mostly wait for them to engage to stabilize.
Can you just repeat the question?
Oh, yeah. I was just wondering, there's always a huge number of fission products that come out of the reactor. What do you do to dispose of those things? They would keep them around until the radioactive ones would not be disposed of until they become unradioactive. Most of them decay down to stable isotopes within about a decade. But then the ones that stay around longer than that, they just get stored. That's the way it's done now with these light water reactors. We have thousands of tons of material that's come out of these reactors that's just essentially temporarily stored. It's long-term temporary storage, but it's so yeah, basically you store it. You wait for it to decay. Well, he's saying it takes 300 years for the stuff to decay. Nobody can go near it. Well, you take this spent fuel and you take it to a reprocessing facility, separate out the stuff that's still radioactive, and then it's put in some sort of storage facility. There's places that have been designated, like there's a place in California, the Yucca Mountain place where they want to do long-term storage of these radioisotopes, and you leave it there. At present, they're storing this high-level stuff from the light water reactors, and it's not even being separated. That was another thing I didn't really mention. These chemical separation systems can actually be used to separate the stuff that we've already made from the light water reactors. So, but the answer is no, you can't go near it. It has to be secured, someplace where it can't be gotten here or stolen. I don't see you had a question. Well, I don't know the details of the process, but it hits the nucleus, and you know, the strong nuclear force is what binds nuclei together. So it's the attractiveness of that force that there's a lot of quantum mechanics in the dynamics of the absorption, which I don't understand at all. But yeah, many nuclei can absorb neutrons. Sorry.
Well, actually, I've got another question. Wow, how much traction is this new technology getting in various places around the Earth?
The Chinese government is building a pretty large test reactor, and it's actually a power reactor. It's not the full-blown version with all the different salt systems, and it's, in fact, I don't think that fuel is in a liquid form. The liquid has these pellets in it, which contain the fissile material. And I can't believe it's not a full-blown system, but they're definitely doing research on it. And there's a couple other countries that are too. But in the United States, it's only really, the government isn't really forging toward it at all. It's being pushed pretty strongly by proponents of this, which is how I found out about it. Mm-hmm.
Mr. Pierce said more about the corrosion problem. I know it involves a lot of reactors. They have tremendous corrosion problems. How do those, how are the problems with the oil fast fluid compared with those problems with corrosion?
It's different problems, I know, because in the uranium reactors, in the light water reactor, the fuel is solid, and so the fuel pellets are actually damaged, and they get cracked and everything. That's one of the reasons why they're doing it their lifetime. I really don't know much about the corrosion problems that they're facing with this technology, but I think it's a whole different set of problems because of the fact that the internal structure of the reactor is so different.
They also had some problems with not the, what I want to say, the shell of the reactor seemed to want to corrode it too. I don't know what it is, escape from a blanket or what.
I mean, like that.
Well, I got the impression that they were looking at the neutrons themselves, getting into the shield and cracking them as well.
Yeah, to tell you the truth, I don't really know much about how all that stuff happens.
And I was wondering if that applies to the thorium reactor.
I would guess, because I mean it's fission with neutrons.
One other comment, up until the Japanese got the containment done in all those debris and Chernobyl was a result of no containment done, whatever. Chernobyl is no containment.
Yeah, right.
It's totally irresponsible.
Yeah. There was some big slab or something. It was something like a containment. But when the reactor exploded, it bumped that thing up and then it fell back down.
Yeah.
And it just, yeah, it was. There were numerous design problems with Chernobyl. The control rods, when they had the control rods pulled out because there was a test going on. And when the reaction started running away, they dropped the rods down, and that actually caused a neutron spike. Because there was, I can't remember, what something about the rod. There's a tip on the end, and when they put it in, it's designed to, get the reaction going. I can't remember how it works, but it's designed. It broke a lot of rules too.
Yeah, you usually have CAD balls, I think it's doubt that something like that happens. Apparently, the electric didn't have anything like that.
Yeah, I don't know. Yeah, I know that. I can't remember what it is. There's something about the design of the control rods that would probably cause the runaway because they were trying to reinsert them when it occurred. And when 3,000 megawatt reactor went up to like 30,000 megawatts in a couple of seconds.
You want to come a little closer to the microphone?
Oh, yeah.
I was wondering how fast the fast neutrons are going to the speed of light, compared to the thermal.
No. With rapid relative energy, so this is EV. So 10 million EV for a neutron. Can you figure that out? How fast does that correspond? I assume is that relativistic? Probably. I mean, carrying. That's a good question. I can't calculate that in my head. 10 million EV for a neutron. 7 times 10 to the minus 27 kilograms, and an EV is 1.6 times 10 to the minus 19 joules. Is that right?
Oh, I
don't have a calculator. Yeah, probably not relativistic, because that would be.
Neutron is pretty significant amount.
Yeah.
Compared to photon or neutrino.
Yeah, if it was relativistic, that would mean that it's going near its rest mass, which there isn't that much binding energy in there.
Yeah, I doubt it. I think that we have to put a lot of energy into the neutron to speed it up. How.
Yeah, but I guess that's when they leave the nucleus, they're doing that speed, and they're moderated down to somewhere in here. They turn into thermal neutrons, which is, in other words, after they keep bumping into other nuclei, their energy is like the background energy of the temperature of the reactor. Let's say it's at 600 Celsius, so they're moving, the speed is distributed on the thermal spectrum. So that's why they call it a thermal breeder reactor, as opposed to a fast breeder reactor, which is what they tried in the 70s. Where they're still going really fast.
Any more questions?
I wonder, just speculating, I wonder, we always refer to them as pop neutrons rather than thermal, rather than fast neutrons. What are those distinctions that I should be making?
I don't know. Maybe prompt.
They talk about pop neutrons as if they were, fast neutrons. And when anybody said pop neutron, they later became fast neutron. I just wondered if there really was a distinction.
I don't know.
I treated them the same.
Oh, really? Yeah, I don't know. Your question. What I was reading, I just read fast, because they called it, back in the 70s, they called it the fast breeder reactor.
No.
The U-238 breeder reactor. And one thing I didn't talk about is that U-238 breeds into plutonium-239, which is exactly the right stuff for nuclear weapons. But thorium breeds into uranium-233, which actually doesn't lend itself to use in nuclear weapons. I mean, that's an advantage. You see a disadvantage, right, during the Cold War. But now that's considered an advantage that might allow this technology to be developed, because nobody wants to, proliferation anymore. And so there's something about, I guess U-233 can be used in nuclear weapons, but it's poisoning with 232, which is very radioactive and makes it traceable and dangerous to work with and all this.
It's quite complex to live in nuclear weapon. It's too rambunctious, let's say, then you don't get a chain reaction. Because it gets too hot and bombs fly apart and vaporize it before you get a chance to explode it.
Right.
So not everything is suitable for, making a bomb. You get all the detonation.
Yeah.
And so,
I think 233 was used in some U.S. tests So they used some 233 to test it, back when the testing was being done in the 50s. I don't know much about whether it worked but anyway, one of the selling points is that U-233 just does not lend itself to nuclear weapons. But,
Okay, if there's any questions, thank our speaker for today. Okay, so we do take with our new technology, so obviously we'll have to work out some of the snacks, but hopefully we'll get there.
snakes.
Okay.